It looks like it just started, so I'll let me stop presenting and to turn this off. And go ahead when you're ready.
Can you see my screen? Hello?
Unmuted us. Yes, we can see your screen.
I'm muted?
No, you're not muted. Go ahead, and we can see your screen.
Oh, you were muted. Okay. So hi, everyone. I give a talk called "So How Does Crystal Do Its Magic?" Here we'll see how Crystal is implemented, some tricky parts, and challenges to implement also some tricky parts of it. And to start, I'm going to start with this question. So what's the single most used feature in Crystal? And I thought about doing this interactive, like maybe you can type something in the chat, but I have like 100 slides and 45 minutes, so I'm afraid maybe I'm not going to fit them all. So it's not going to be interactive, but I gave you some time to think while I said that. So here are some options. You have, is it macros, methods, maybe structs? Is it type checks, like if something is a something, or is it something else, like type of work? Something else, not because it's not in the slide, but what is it? So the answer is methods. Methods are everywhere in Crystal. So for example, if we take a look at this method, the plus operator for string, which lets you concatenate two strings, can you spot the methods? And when I said methods, I mean methods and also method calls. Can you spot them? They are here. You have empty, you have new with a block, you have copy from, you have to unsafe, byte size, even plus is a method. Even the plus method in string is a method itself. So methods are everywhere in Crystal, and that's the thing that you use most of the time. And I mean, they are everywhere. So methods, they are everywhere. And because they are everywhere and we use them all the time, in Crystal, we wanted to make them powerful and flexible. So because you're going to use them all the time. And we want them easy, intuitive, and fun to use because they happen a lot. Almost like in Ruby. And I say almost because Crystal wants to keep most of the things from Ruby, but because of the limitations of static typing and some other things, it's not possible, but we almost want to be like in Ruby in that sense. So how are methods implemented in Crystal? One thing to know is that Crystal compiles to native code, so it will generate an executable native binary, which essentially means that we want to generate assembly code for a particular architecture or target machine. And we use LLVM for that. So what's LLVM? LLVM is a language that is similar to assembly, but it's a bit more higher level, and you can think of it maybe like C. I don't know. It has, it's mostly like assembly, but you have functions, and you have types, and you have some operators. And what LLVM does is, if you are a compiler implementer, you can, instead of generating assembly for each of the architectures, you generate LLVM code, and LLVM takes care of knowing how to convert that code to the different assemblies for the different architectures, which is nice because you just need to worry about LLVM. And LLVM has something really cool that it can optimize the LLVM code that you generate a lot. And when I say a lot, it's really a lot, and Crystal relies on that. And something really nice too is that LLVM is continuously developed, like it's developed right now, and they keep adding optimizations and more platforms. So that's great. So Crystal generates LLVM code, or we want to generate LLVM code. What's function in LLVM like? So here's an example, and don't worry about this. Like, there are many operators. We won't like dive into LLVM. It will be just 2 slides. But to give you an idea, you use define for functions, and then here you can see that the return type is an integer of 32 bits. And this is the name. These are the arguments, which are also typed. Then you have a block. Then you have another operation, which we assign it to this strange-looking variable, which is actually not a variable, or yes, you can't reassign it to it in LLVM. And then we return the result, which is also typed, and it must match the function. So you can see that types are required everywhere in the LLVM function definition. But if we take a look at the method in Crystal, you have this, and there are no types. So Crystal's job is to go from this, where you don't have types, or at least you can see them explicitly here, and generate LLVM code. And we'll take a high-level overview of how Crystal does this. Yeah, as I said, we need types to generate LLVM code, which eventually will go to the native code. So how are methods implemented in Crystal? So, and this is very important. One thing to know is that in Crystal, every method is a template. Even if you specify like type restriction or return type, the compiler will treat it as a template, because maybe the restriction, we call it restriction because it restricts the types that go in, but when the instantiation of that template might have like more specific stuff to it. So I said that every method is a template, and this template only gets instantiated when you call it with something. So in this case, for example, if we do $1, the compiler knows, like it's one of the basic rules in the compiler, that an integer literal has the type of int32. So from here, the compiler will do this. It will generate a method, like it will copy this, or it will instantiate this, and it will generate a method with this name, where like it's a different name. It has the type of the argument. It actually also has the type of the return value, but for now I kept it simple. And it will say, OK, you're calling double with x, and x will be an int32. And from this, the compiler will be able to like type the body. And it will say, OK, this is an int32. And to resolve this, we need to search the plus method with an int32 argument, and it will do that recursively until it finishes, or it stops when there's a primitive that we say, OK, we know this is typed like this. And then it will say, OK, this method call is bound to this specific instantiation. And then at that point, we are ready to generate LLVM code because we have all the types that we need. So that's essentially how the compiler works. It's a bit more complex because like computing the type of the body, you might have assignments, if, loops, and it gets a bit more tricky, but that's the general idea. And you can see, like, if you take that program and compile it with Crystal and pass emit LLVM IR, it will generate the same program name but with an LL extension. And if you dig into it, you will actually find that instantiation. It's actually called like this. It has a star in the beginning. And you can see, because we recently added overflow, add with overflow, but by default, you can see it's doing the add overflow. And then, like, if it's overflowing, it raises, and otherwise it returns a value. But this is not important. This was just to show you that this is what actually happens. OK, and that's everything we are going to see in Crystal in this presentation related to LLVM and generating code that has lots of symbols, and it's hard to read. So we said that methods in Crystal were everywhere, and methods in Crystal are really powerful. And what I mean by this, I mean that in Crystal, a method can have default arguments. It can also have named arguments. You can have splats. I'll go over that later. It can have double splats. I won't go over that, but it's similar to how splats work. We also have the special or the magic constants file and line, which we can use in default arguments for a specific behavior. And methods have blocks. So you can see that methods are very flexible and powerful. And we wanted them to be like that because it's one of the things that you use most of the time. And we'll go over some examples for each of these, except double splats, and think about how we can implement them and how Crystal eventually implements them. So let's start with default arguments. Before that, I hope I'm not going too fast, but if I am, I guess you can review this video later. And of course, there will be a space for questions at the end. So default arguments, how to implement them. So, but first, what are default arguments? So this is an example. We have a method called div, where we have a required argument x, and this second argument has a default value of 2. So we can call it, it simply divides the numbers. We can call it to 10, and the result will be 5. But what transformation does the compiler do to this to achieve this behavior? Like, how does it work? Any ideas? Of course, I won't make it interactive, but you can try to think about it. And maybe the first idea that comes to mind is that it's easy. Like, the default argument is 2. So if we don't have it in the call, we just stick it in the call, right? We put the 2 here, and then the compiler, the only thing that the compiler needs to do is have a single method that always requires those arguments. And whenever it's missing, we stick the value here. Well, that's a good first approach. But what happens if we have something like this? So in this case, we have a class. And for the default argument of divisor, we have this default divisor that's a method on foo. And it returns 2. And now we instantiate a foo, and we call div with 10. So if we try to do the same thing as before, like we somehow put here the default argument, this doesn't work anymore because like default divisor is not defined here. And so this is not good. So how can we fix it? And one way we could fix it is to let the compiler like, okay, I'm calling this method or this method, or actually this one, in the context of foo. So let the default argument be resolved in that context, like instead of at the top level. And a way to write that or not model that would be to do it like this. So, and here I split it into 2 lines, but calling default divisor. Maybe that's better. But let's consider this case where we have 2 classes. So we have class foo, which has this method div, and it has a divisor, which is default divisor 2. But we have bar, which has magic number for divisor, and it's something different. And then we create an object that can either be foo or bar at compile time, and we call div on it. And I'll explain this because maybe some are not familiar with Crystal, but in Crystal, in this case, Crystal supports union types. So here, object for the compiler can either be foo or bar. And you can call this method div because it's defined for both foo and bar. And at runtime, it will, depending on which one is it, it will call one or the other. So default arguments, we said about copying this or this in the context of like the call, but it's a bit more complex, right? Because now it depends on which one you have. And maybe we can say, okay, resolve it in the context of object. and then do a dispatch to the correct default value, but it's getting a bit more complex. So the way we implemented this is by, so when you call this method and it lacks this argument, the compiler will generate another overload for it, where the argument is actually missing, but it's inlined inside of the method. Okay, and then we end up calling, and this ends up calling the other overload. And then this call only needs to pass the argument, the required argument, which will be filled in the in this overload. And if you have multiple dispatch, this expansion will be done for foo and for bar. So we basically delegate the default argument to each class in a separate overload. And something I forgot to say is that for implementing all of this, we didn't take a look at other languages, because Crystal is pretty unique in what we have, and what it has, like union types and multi-dispatch. It's not common in other languages. So we didn't look at how to do it in other languages, because they don't do it like that, and they won't support our use cases. And this is what we ended up doing. But if you have like better ideas or different ideas that might work, we would love to know about them, and you can open an issue in GitHub or discuss it in the forums. It's pretty interesting to think about how to solve these things. So this is how we solve default arguments. And did you know that Crystal is statically typed and compiled? And other languages that are statically typed and compiled are, for example, Java, C#, Rust, Go, NIM, and Haskell. And let's take a look at briefly at each of them to see like whether they support default arguments or not, and how. So Java has no default arguments. C# has default arguments, but they must be compile time constants, which means they must be integer literals or strings or a mathematical operations, that a mathematical operation like 2 + 2 that the compiler can resolve, or a constant that has a value, but it's a constant. And my guess for that is that if default arguments are compile time constants, then you can do the trick of putting that value in the call when it's missing, because you won't be resolving method calls and so on. So that simplifies the language, and it simplifies the job for the compiler implementer, but it's less flexible for the users. Rust has no default arguments. Go has no default arguments. So you can see that many languages don't have default arguments. They don't want to deal with this complexity, or maybe they want to simplify the language for the users, but give them less power maybe. And NIM has powerful default arguments. I didn't code that much in NIM, but I tried like doing a default argument that called another function, and it worked. So my guess is that it works great. So yay for NIM, which is great. And Haskell has no default arguments, but Haskell, it's a bit, there's a mosquito in the room, so sorry if I make like some things. Haskell is a bit different because it's functional, and I won't go too much into detail, but to explain it, in Haskell you can have a function with 3 arguments, and if you call it with 2 arguments, that succeeds, but it gives you a function that still awaits another argument, and you can do that with every function. And if you want to mix default arguments, imagine you have 3 arguments, and the last one has a default one. If you call it with 2 arguments, do you want the 3rd argument to be filled with that default argument, or do you want and call it, or do you want to have like a partial function ready to call? So there's a conflict there, and my guess is that there won't be default arguments in Haskell or functional languages with automatic partial application. So we took all the trouble to have like these powerful default arguments. Why do we want to have that? And the reason is that we want to be more expressive. If you can, for example, in Java or in other languages, what you can do is define an overload. Basically, what the compiler, what Crystal does, it defines define an overload and call the other one with the default argument. But you have more boilerplate. So with default arguments, you also have less boilerplate. And you only need to use a single method name. So for example, Go doesn't have overloads, and you can have two functions with the same name. Even if they have different arguments, you can do that. So we end up having to do, you have to make up new names for the things that you want to have more arguments and so on. And this is not a critique to any language. I'm just saying how things work in different languages. And what I see as, I don't know, making things, giving more power to the users. So next topic is this magic file and line constants. I think, I'm not sure if they are in C or C++. I don't know. But the way they work is if they are not in a default argument position, so they are not the value of an argument that's used by default, the parser expands them right away. The parser knows which file and line you're in, so it will replace that directly, this with a string literal, with a file name, and this with an integer literal. However, if they are in a position of the default argument, they are expanded on each call side. I think, yeah, and this is an example. So, sorry. You have this method foo that requires this argument, and this is optional. And if you don't specify, but it has this value, line. And if you don't specify it, this is line 1, 2, 3, 4, 5. So the compiler will pass for line number 5 here instead of like line number 1. That's the value here. And this is nice because you can know the file and line number of the caller. And for example, we use it for the spec library to know where an it block. You also have like end line to know, for example, if you call it with a block, an it block knows where it's defined. So later you can run it by saying, I want to run spec files only on these lines, and it works. And like, it's a really simple and powerful feature for those things. So, and the question is again, how do we implement this? How do we implement default arguments when they have this value? And you might think, well, maybe it's similar. Like, we could inline this value here, but we already saw that with multi-dispatch that won't work. And this is an example, for example. And maybe in the other overload of foo, you don't have like the line number. You have 42. So it's a totally different value. But if we try to do the trick of expanding this to a different overload that receives an X and passes line, that line depends on the call. Like, you can't put it inside the other overload. It's a bit tricky. So the compiler will actually do something slightly different here, maybe a bit of magic, is that foo, in the case of this special default arguments, the compiler will, for this overload, like here there will be a dispatch. For this case, it will do what we saw earlier. But for this case, it will still call this overload, and it will fill this value with a magic value, but on the dispatch of this. So I can't write it well. And then on the code generation phase, let me see. Yeah, on the code generation phase, the compiler will replace those magic values or special values or dummy values with the line number. So there's a bit of magic here. It's a bit different, but it's similar to what we saw before. And I put a picture of Freddie Mercury because whenever I say it's magic or hear about it, I can imagine him saying that in It's a Kind of Magic song. I don't know why. Also, maybe his voice, maybe it's a bit magical. So did you know that this supports the same thing, file and line in default arguments? So guess who was our inspiration? And then Swift has that feature too. And at this point, we don't know what was their inspiration, maybe D Crystal or something else, because you can also do that, like use them in default arguments. Let's move over to named arguments. I hope this is not too dense. Like, there are many cases, there will be similar, but they are slightly different. So Crystal supports named arguments for all arguments. Let me look at the time. Okay. I looked at the time, but I don't know what slide I'm in, so maybe not very useful. But Crystal supports named arguments. So we have what we can do for all arguments. What you can do is call this method like this. We put divisor here 3. Or you can also specify that you want to call x with a named argument, and it's the same. Or you can even swap the order of the named arguments, and they are the same. So how do we go about implementing this? And the first thing that might come to mind, again, is that the compiler will simply need to rewrite this. Like, okay, say, okay, this matches the same order as this one, so I just rewrite it like this. This same order again, I just rewrite it like this. And this has a swapped order, so we swap the arguments, right? Pretty easy. Well, but what about multi-dispatch again? Because we might have, I didn't explain this in the other slide, so I'll explain it now. But oh no, yes, I explained it, but this is slightly different because it's creating an array of foo and bar, and for each it's calling div with x and divisor. And here again, object will be a union type. So there will be dispatch. But you can see that the arguments here are x and divisor, and here it's divisor and x. And so there's no way for the compiler to like say, okay, I'll rearrange the argument for what? There are different arguments in the call side. And at this point, one might think like, but really allow this case, like what's the use case? Why is it used for? And for us, it's most a matter of having a sound language, like what you would expect this to do. And I would expect it to do what you would expect it to do, like put the things in the correct order for the overloads. And if you try it, it works. And if there's a way to make it work, then it's more intuitive. We don't have to deal with users maybe reporting a bug that this doesn't work, and we have to say, well, it's hard to implement. There's no use case. Maybe there is a use case. Maybe you have two classes with slightly different arguments order, and you want to unify them without creating a wrapper type. I don't know. But yeah, how do we deal with this multi-dispatch situation? And we can see that multi-dispatch is starting to like appear in multiple places. So what's really multi-dispatch? And it's pita. And pita is this bread that it's look very simple and easy to eat. But once you put stuff in it and it starts interacting with with other things, it's like unwieldy and you can't hold it and everything spills out. So that's what multi-dispatch is, at least for a compiler implementer. For the user, it's great. So let's go back to multi-dispatch. How do we resolve this? So we said we can't resolve it on the call side. So we use, again, the same old trick of creating new overloads. And in this case, it's a bit different. For the case of foo, you can see that x and divisor have the same order. So the compiler will say, it will still do a dispatch here, but for the case of foo, it will call this method, and there's nothing to do. Like these named arguments disappear. The order will always be 10 and 3. And for this overload, it will call, or for this dispatch, it will call this overload. But for bar, it will generate a different method that has this x divisor, which means the argument come in this order. and this overload or this dispatch will end up invoking this. And this is fine because like it's a generated name by the compiler. It has these columns. You can't write it in Crystal, so it can't conflict with the user-defined method. Like if we use the same name, it would conflict already with the other one. And this method, what it does, it passes it calls the other overload, the original overload, but putting the arguments in the correct order. And again, there's a bit of magic because this ends up invoking this one. And so yeah, again, there's a bit of magic. And you might be worried, but well, the compiler is trying to generate a lot of method call, a lot of hidden overloads. Won't that affect my code performance? And the answer is maybe, but LLVM is pretty good at inlining stuff. So what we hope is that LLVM in the end will just for that dispatch end up calling this one, this one with the correct order. Like it will figure it out. And that's what usually happens. So don't worry about it. Like we delegate things to LLVM and it works pretty well. So it's magic. Next, splats. So what are splats in Crystal? You can have an argument with a star in the front. You can have other arguments, but one of them can have a star. And that means that you can call the method with multiple arguments. And what ends up happening is that all of these arguments will be packed as a tuple and passed to this method. So when you're inside the method, you see the arguments as a tuple. A tuple is a bit slightly different than an array in that the compiler knows what type is in each position, and it has a fixed size. So they are very handy for certain things. So how do we go about implementing splats in Crystal? And again, one idea that you might have, but now you probably think, but wait, there's multi-dispatch, something is going to be wrong here. But one idea that we could do is like, okay, the compiler rewrites the method call by packing the tuple and passing it to the argument. So this actually never receives a splat. It always receives a tuple and the argument, and the compiler packs the arguments in a tuple. But what happens if we have a multi-dispatch? So we could have foo and bar. Foo receives a splats, but bar just simply receives the 3 arguments. And then for an array of foo and bar, we call foo, and this is a shortcut syntax for calling foo on the first argument of the block. And if we try this in Crystal, it works, like what you would expect to happen in Ruby, for example. So we want that to work in Crystal. So here we can't pack the arguments anymore, because if we pack them, yeah, it works for foo, but it doesn't work for bar. So what do we do? So again, we use a similar trick. That's the compiler will, if we have a method with a splat argument, when you call this with 3 arguments, it will generate a method that has the arguments in position. Then it will pack them in a tuple and then call the original method. So, and the nice thing about this is that it works in the multi-dispatch case, because every method in dispatch always receives this number of arguments. And if you have different types, this will be like what we saw before, that when you call this will generate an instantiation of this. Still happens. So if you have different types, there will be different instantiations. And this works. And one clarification is that sometimes the compiler will choose to inline the method body, like the original method body, instead of delegating and calling it for some reasons. I can't exactly know why, but there were some cases, and these are splats blocks, like when you do yield and so on. Just in case, like if you generate LLVM code and take a look at what's going on, for this particular case, it's not calling this one, it's inlining the body. but it's in the end, it's similar. Like as a user, it's both ways have the same result for you. And if you have overloaded splats, so you can, in Crystal, you can say, I want any number of arguments, but all of them, I want them to be integers to be covered in this case. And anything else I want to cover in this overload. So this one will end up invoking this one, and the second one will end up invoking this. How do we implement this? Because you need to, like the bodies can be different, this and this. So the compiler, again, will generate for each of the original overloads, it will generate, and you can imagine, this is not exactly like that, but you can imagine generating an overload where each argument has a restriction on the types. So, and the R1 doesn't have. This slide in particular is not doesn't add much, but that's how it works. And yeah, it's Twitter time. Luis Lavena asked me that he said that if I didn't show this meme, then the talk didn't happen. So it did happen. So Splats, again, did you know? Did you know that in most programming languages that support Splats, the splatted values must all be of a single type, and they are packed as an array? What the first thing means is that if you pass multiple values, you can pass an integer, a string, and a character. You always need to pass like either all of them must be integers or all of them must be strings. And what you get in the function is an array, which I guess it's fine, depending. I was thinking, like, if it's an array, it probably needs to be allocated on the heap, because maybe someone keeps a reference to that array, so it can be allocated on the stack like we do with tuples. But that's not, well, that's one reason why we chose tuple. Another reason that we chose tuple for Splats is that you can forward arguments and have everything work, or almost like in Ruby. So for example, imagine you have this method find haystack needle, and you want to know the index of a needle from a haystack. And these names I copied from PHP docs. You can define a find with logging method that accepts no matter what arguments, you don't care about what arguments you receive, and you log them, and then you call the original method by, again, splatting these values, so putting them in order again. And because the types are preserved, this works fine, and you can pass a string and a character. They come here, and this will be, again, a string and a character. If it were an array of single types, you wouldn't be able to do this kind of thing. So that's why we chose that. And that's good and bad. It's good because there's no heap memory allocated. Essentially, that means it's faster, and it doesn't put pressure on the garbage collector. But there's one method instantiation per different tuple type, like what I mentioned. Like if you pass 3 arguments, there would be a specific overload for that. If you pass 6 arguments, another overload, and so on, which might bloat the generated code, but probably not, because LLVM will like compact things and inline things. So it's fine. Finally, I'm going to talk about blocks. I won't go into details of how they are implemented, or briefly go about that. But I want to talk about blocks because they are super interesting, and they happen in Ruby, and they are a great idea. So blocks are this. This is a block, and you can define a method. This is a summary of blocks. Then it will get a bit more interesting. You can do yield 0 and yield 1, and you can call twice with the block. What ends up happening is that this body of the block will be executed first with 0 and then with 1. And some languages don't have blocks, but have callbacks. So you could write it like this in other languages, and in Crystal and Ruby too. Like you receive a callback, which essentially has a call method, or the callback is called proc or lambda in Ruby and proc in Crystal, and maybe function point or function literal in other languages. So you receive this callback and you call it with 0, and then you call it with 1. And for twice, we pass the callback function that receives an integer, and then we print this. So what's the difference between blocks and callbacks? Like, why do blocks exist? Are they the same? Like, other than this maybe being like, clearly there's more code, like it's more verbose. So callback is already a long word, and you have these symbols and like parentheses. The parentheses could be omitted, but is there a difference more than the syntactic aspect of it? Like, did you ever stop and think about like what's the difference? And we'll see it with an example. So we have our lovely twice method that yields 0 and 1, and we have this just once method. And we call twice with the block, and if x is 1, we return ha ha ha, or just ha ha. And at the end of it, we say, I thought we were doing this once, and we print this. Can you figure out what gets printed in the end? Yeah, it would have been nice if this was interactive, but now let's see it with, but I'll give you some time to think about it. Now let's see it with callback. So we have the same code, but with callback. We have callback 0, 1, and we call twice, and we pass a function literal or a proc, and we do the same. What's the output in this case? Like, is it the same? I would expect it to be the same, right? So it turns out that no, they are not the same. And the difference is that this is like this return, because this is a proc or a function literal, it's returning from this function. So so twice will be called, and then I thought we were doing this once will be returned. However, for the case of a block, return kind of escapes the block, and it returns from the method. And there's also break, like you can break from a block, or you can next, like ask for the next iteration. And that's like the single most important difference, is that return and break and next lets you, like, it keeps the flow of the method like what you would expect it, and it makes block, like it lets block enhance the language with the DSLs or with flow or control structures that make it look like this is a keyword or this is part of the language, but it's not like I'm passing a callback and so on. So I wanted to mention this because I think like the difference is really good, and I coded in Ruby for a long time until realizing like this huge difference, which is really nice. And for example, here we have the spaceship operator for array for comparing like the order, how they are comparable. And we have like an up to, do, and if there's a condition, we return. And we never stop and think about like, yeah, like this is a callback or something like that. It's natural. It's like you read the code from top to the bottom, you know that return goes here. So that's something super nice. And regardless of implementation of this, what the compiler ends up doing, whois for blocks that you don't capture, is inlining. So for example, in this case, it will inline this here. It will actually inline it here, like it will do this twice, 1 for x0 and 1 for x1. So it will always inline the method that you call, and the body will put the body in the yield positions, which also gives you a really nice performance. Like you can do 3 times and it's the same as a while loop. And blocks. Did you know that Kotlin has something very similar to this? They added it recently, I think, that you have, like, they have callback functions, but you can say, I want this to be inlined. So similar to what Crystal does. So Kotlin, really nice that they have a similar feature. Okay, I guess I'm 5 minutes late, but I guess it's fine. So we went to like some challenges or some interesting parts, I guess, over how to implement some things. But my conclusion is that Crystal is ambitious. We want to have this very flexible and powerful methods and features in the language. And Ruby is ambitious too. Like if you think about it, Ruby is, I think, 25 years old or 20, I don't know, something like that. So it was created in a time where computers weren't that as fast as now. And thinking about that, a dynamic language that, like, at that time, I think it was pretty slow, but like Mats said, I guess, I don't know, he said, like, but I want this to be powerful. This is the way I want to program the computer. And if it's slow, if there are problems, if it's challenging, I don't care. I don't want to like restrict the user. I want to try to make it work and hope that in the future I'll make it work and we'll make it fast. And that's exactly what happened with Ruby. Even though like there are some limitations, they still keep working that. So with Crystal, we have the same philosophy. We try to make the programmer happy, and we let the compiler, implementer, or interpreter implementer worry about that. And I think that everything can be solved with time, effort, patience, and love. And I wanted to include a reference to a song that I like. It's in Spanish. It's called Algo Está Sucediendo from Sandra Mianovich, which was also an Argentinian singer. And the lyric and the music are really nice. This is linked for an English translation, which is okay. I think this applies in general to life or life situations, but I always relate it also to Crystal, like as a project or something. So you can take a look at that later. The slides will be published somewhere later, or you can copy from the video, but from the slides, it will be fine. So I hope I wasn't muted this whole time. Thank you for
you weren't muted.
For sharing this moment with me and watching.
Thank you so much. I actually have some questions. I'm not sure if other people have questions they want to. Does anyone else have any questions?
I also have this one, but I guess.
Yeah, you're on.
I'll stop sharing. Or
right, you're on.
Oh yeah. No, I thought you had a question. I was gonna say when methods are added, they're like generated. Where do those methods go? Are they in the IR files that are like emitted? If you do the Crystal that file -- emit LLVM, like how do those like generated methods, like are they inside the classes or something?
Good question. So the compiler will initially parse the methods, and like it will have these methods, and then when you call them, like each type has a hash of method instantiations that are related to methods, and they are stored in memory until you generate the code. So if a method instantiation ends up being used, and this method instantiation could have been resolved, could be the result of this method, this expanded method that I showed in the talk, then yes, they will end up in the generated LLVM code. And you can always generate LLVM and try to take a look at that and find, like, if you try to find a function name or a method name, you will see all the different instantiations.
How does the debugger handle that? Like, if you step through something, does it just jump to like it wouldn't jump to like the generated code. It would just like jump to the actual function being called.
It's a good question. So the generated methods, every piece of grammar in the language that's called AST, Abstract Syntax Tree, has a location property that results from the location in the parsed file. And when we instantiate methods or do these generated methods, we always try to make sure that whatever we expand and whatever we generate keeps a reference to the original location. So when you are debugging or when an error happens, compile errors happen in instantiation or generated methods, but because the location points to the original methods, yeah, they will point to the original methods, and that will be transparent for you. Except for the case where I'm thinking about it now, remember that for the named arguments where we swap the order, the compiler generated a method that's called like, I don't know, foo colon, increment colon, or something like that. You will see those in the, like in stack traces or when you get an error, no, but yeah, that's the detail. We could improve that, I guess.
And then the other one I had is like the list of features for methods I find really impressive, especially for a compiled language. But do you have any future features that you want to add to methods? Like, is there any plans for more things to methods?
Again, great question. Yes. Well, so the first observation is true. Like when I think about it, what other languages have like statically typed and compiled languages have this many features for a statically typed and compiled language? I don't know if there's like another such language. Maybe yes. So that's like, I think that's it was nice to be able to achieve that, I guess. And what other missing features? So there are some things that could be implemented, but they don't have like high priority, but it could be implemented. One thing is there's a difference regarding blocks. There's a difference between when you yield and when you capture the block. And when you capture the block, when you yield, because the method is inlined, you can do some kind of recursive thing. For example, if you have a tree that has nodes, child nodes, and you want to yield each of the values in the node, it's like you have to yield recursively. I should write it, but I'll probably get it wrong. But it doesn't work. It works in Ruby, but it doesn't work in Crystal because everything is inlined. Like you can't call it recursively because it will end up in an infinite expansion. And there are ways to solve that. Like because the block isn't captured, we could create a closure and pass it. It's a bit complex, but maybe it would be nice to solve that limitation. Another thing is Python recently added a way to, so the way method arguments work, they didn't work like that all the time, and eventually we said we really like the way Python works, and so we did it similar to Python, but it's mostly inspired by Python. And Python recently added, I think you put 2 slashes after positional arguments, and that means that the arguments before those slashes can be called with a named argument. And the use case for that is, for example, if you have a math operation like ups. Well, ups is a method from int, but in Crystal, but logarithm, log2, or which belong to math. The argument, it's just one single argument. Maybe it's called x, or then the name of the argument doesn't matter. So maybe it's not good if we allow users to specify that x, because it ties the call to the implementation. If we later decide to give that argument a better name, it will break code. So a way to preventing passing those arguments as named arguments would be nice, maybe, but it's not like super needed. It's nice. It's a nice to have. I guess at this point, everything is nice to have because what you want to do, it's pretty good. Related to methods, at least.
That's pretty interesting. I have been asked more than once if Crystal supports functional programming. I like never know how to answer that because it's design in O, but I'm curious if the like recursive stuff would be like a limitation. I don't really know. Yeah.
Yes.
Hi. So, speaking of nice to have, when you were going over named arguments, and you were talking about, oh, what would you expect this to do? Because I didn't know this particular syntax yet, I expected it to do something very different than what you said, because I write Ruby.
Okay.
And it's very nice. It's very nice to have. It's very nice to have named arguments, but it's using the exact same syntax as Ruby's syntactic sugar for passing a hash to a hash as an argument to as somebody who's trying out this language in no small part because of how similar to Ruby it is, do you have any advice about other things I might see around that look exactly like Ruby that I should read very differently?
Yeah, good question. It's true that it's like if you come from Ruby and see that, you would expect that to fail, because in Ruby, I think you would expect X and divisor to have a colon in the method definition. So things I would recommend is,
I mean, other than the fact that I'm just going to read, I'm going to read the
read
documentation.
The language reference, because there are the most differences. But maybe another way could be, well, that particular syntax thing, I don't know, like how you would be able to conclude that in Crystal. Like some other things, for example, splats that you can forward. Maybe thinking about static types, you could think that they work like that in Crystal, but it's I don't know if that leap is possible automatically. I guess differences will come clear once you start using the language and know the differences, and then you learn them, I guess. Unfortunately, there's no other way than stumbling upon those differences and learning the differences.
Just don't just copy paste it and then run it, basically.
Well, actually,
don't just run. Some of my Ruby you can just run, but don't always just run it.
There's actually a fair amount like that does, but there's a fair amount of like simple things. I think if anything is under 30 lines or something like that, a lot of those things you can copy paste over.
Yeah, you can still copy and paste, and probably in Crystal you will get an error, and then you can go ahead and start fixing things, and that can work. But Crystal, like in the beginning, we tried to make it as compatible and as similar to Ruby, but at one point we diverged, and after that point, we consider it as like a new language, something different. For example, Elixir. Elixir is super inspired by Ruby, but you can't copy a Ruby file and paste it in Elixir. Like it took some really nice things from Ruby, but it's still a different and its own language. And Crystal is the same, except that Crystal is a lot more like Ruby than Elixir, so that might be confusing.
The array of syntax threw me off for a while. If you do like an array, like instead of doing like a type inside parentheses, you can still do that. Like you can just do like array type inside parentheses .new, but it's not uncommon to see an array with just the word of and then like types after it. And for some reason that like I don't know why, just like kind of that's definitely like a difference from Ruby. It's like a different syntax to like get.
But at the very least, when I look at it, I won't have like well-worn neuron pathways that say it's something that it's not.
No, it's not something.
Like I'll be like array of what?
I just forget how to be honest, what happens with me if I want to like use something similar and then write that, I can never remember, even though it's like